Imagine it's nighttime. You quote Ray lying somewhere in the grass or just looking out the window. No city around, just darkness and the sky above your head. And up there, thousands of tiny lights. Still. Quiet. They just exist. You quote V probably looked at them at least once in your life. And you've almost certainly wondered, where did they actually come from? Not in the sense of, well, they're stars, they've always been there. But for real, where from? What was happening before they appeared? What's going on inside them right now? And what will happen when they die? Today we're going to walk that entire path together. Slowly, without rushing. From the very beginning, from the absolute darkness, after the Big Bang, to the moment when you'll understand that you are literally made of something that once exploded in space. It quote us not scary. It's actually very beautiful. Get comfortable. Before we go any further, let's stop for a second on a simple question: what actually is a star? Because most of us are used to thinking of them as dots in the sky. Tiny, distant, pretty, but that's just an illusion of distance. Take our sun. It's an ordinary star, not the biggest, not the brightest, completely average by the standards of our galaxy. And even so, if you could place the sun next to the Earth, you'd see a sphere that could fit more than 1 million planets like ours inside it. 1 million. Now imagine there are stars that make our sun look like a pea next to a hot air balloon. Scuti, for example, one of the largest stars we know of. If you placed it where our sun is, its surface would extend past the orbit of Jupiter. Jupiter would simply be inside it. But size isn't the main thing. What matters is what happens inside. A star is, essentially, an enormous nuclear fusion reactor. At its core, the pressure is so colossal that hydrogen atoms literally collide and fuse together, turning into helium. And in that moment, energy is released, the very same energy that shines down on us from the sky. Every single second, our sun converts around 600 million tons of hydrogen into helium. Every single second. And this process, fusion, burning, pressure, keeps the star in balance. From the inside, thermonuclear fire pushes outward. From the outside, gravity pushes inward. And as long as these two forces are balanced, the star lives. That is what a star is. Not just a little light. It's a place where physics operates at the very edge of what's possible. Now let's rewind everything. All the way back to the beginning. About 13.8 billion years ago, something happened that we call the Big Bang. Though that name is a little misleading, it wasn't an explosion in the usual sense. There was no boom in empty space. Space itself began to expand. Time began. Everything that exists started to exist. In the first seconds, the universe was unimaginably hot and dense. So hot that even atoms couldn't form, particles just flew around chaotically, colliding and scattering. About 380,000 years later, the temperature dropped enough for electrons to attach to nuclei. The first atoms appeared, mostly hydrogen, a little helium, almost nothing else. And then something interesting happened. The universe became transparent. Among those gas clouds, there was no perfectly even distribution. In some places a little more matter, in others a little less. And gravity, patient, unhurried, began to do its work. Where there was slightly more gas, it started pulling in neighboring gas. The cloud grew denser, denser, still denser. Pressure at the center grew, temperature grew. And at some point around 200 million years after the Big Bang, give or take, at the center of one of those clumps, there was a flash. The first star ignited. We've never seen it. It's been dead for a long time, but we know it existed. And most likely, it was monstrous. The first stars, called population III stars, though none of them survived to our time, were nothing like modern ones. Back then, the universe contained nothing but hydrogen and helium. No carbon, no oxygen, no iron, just those two elements. And from that pure fuel, monsters were born. Theoretical calculations suggest the first stars could have been hundreds of times more massive than our sun. They burned bright, burned hot, and for a very short time. A few million years, and that was it. But before they died, they did something important. Inside them, under tremendous pressure, hydrogen and helium were transformed into heavier elements. Carbon, oxygen, magnesium, silicon, iron. The periodic table began to fill up. And then, those giants exploded and scattered all of it across the universe. The first stars, called population III stars, though none of them survived to our time, were nothing like modern ones. Back then, the universe contained nothing but hydrogen and helium. No carbon, no oxygen, no iron, just those two elements. And from that pure fuel, monsters were born. Theoretical calculations suggest the first stars could have been hundreds of times more massive than our sun. They burned bright, burned hot, and for a very short time. A few million years, and that was it. But before they died, they did something important. Inside them, under tremendous pressure, hydrogen and helium were transformed into heavier elements. Carbon, oxygen, magnesium, silicon, iron. The periodic table began to fill up. And then, those giants exploded and scattered all of it across the universe. When you see those photographs from the James Webb Space Telescope, pink, orange, shimmering pillars of gas, you are looking at a stellar nursery. The process begins with a disturbance. Something has to nudge the cloud to make it start collapsing. Sometimes it's a shockwave from a nearby exploding star. Sometimes it's galaxies colliding. Sometimes just an accumulated instability. The cloud begins to collapse under its own gravity, slowly at first, then faster. At the center, a denser region forms a protostar. It doesn't truly shine, yet the nuclear reactions haven't started. But it's already hot from the compression and already gathering surrounding gas onto itself. This process takes millions of years. Around the protostar, a disk of gas and dust forms, slowly rotating. That's exactly the kind of disk that eventually becomes planets. Our solar system was once a disk like that, and when the temperature at the core reaches around 10 million degrees click, nuclear fusion ignites. Hydrogen starts burning. The star switches on. It blows the remaining surrounding gas outward with a powerful stellar wind. And for the first time, it opens to view. A new star in the sky. Every star has its own life. And strangely enough, it depends almost entirely on one single parameter: mass. Mass determines everything: how brightly the star burns, how long it lives, and how it dies. Small stars called red dwarfs are the most common in the universe. They're dim, cool, economical. They burn hydrogen so slowly that they can shine for trillions of years. Our universe is 13.8 billion years old, and not a single red dwarf has died of old age yet. They're all still alive. Our sun is a medium-mass star. It's about 4.6 billion years old. That's something like middle age, the midpoint of its life. It will burn just as calmly as it does now for another roughly 5 billion years. Massive stars are the opposite. They burn fiercely, extravagantly, blazingly. But that's exactly why they live such short lives by cosmic standards. A few million years, like a mayfly next to a tortoise. The mature phase of a star is what astronomers call the main sequence. The star is in balance, thermonuclear fire pushing outward, gravity pushing inward. They're in equilibrium. This can last a very long time, but hydrogen isn't forever. When the hydrogen in the core runs out, the next phase begins. The core contracts, while the outer layers expand. The star becomes a red giant. It literally swells up. That's exactly what's waiting for our sun in about 5 billion years. It will grow so large that it might swallow the Earth entirely, or come very close to it. By then, there will have been no life here for a long time, and that's fine. We still have an enormous amount of time. The red giant doesn't last long in its swollen state, and then it all depends on mass again. The death of a star is probably the most spectacular thing that happens in the universe. Small and medium stars like our sun die relatively quietly and beautifully. When a red giant sheds its outer layers, they drift outward through space slowly, glowing in different colors. This is called a planetary nebula. Nothing to do with planets, that's just how the name stuck historically. It's one of the most beautiful objects you can see through a telescope. At the center, a tiny, dense core is left behind a white dwarf, about the size of the Earth but with the mass of the sun. It slowly cools down, for billions of years. Eventually, it becomes a black dwarf, cold, dark, dead. Though no such objects exist in our universe, yet cooling a white dwarf all the way down takes longer than the universe has existed. But for massive stars, everything is different. When a massive star exhausts its fuel, the core collapses almost instantly. Literally in a fraction of a second. And in that moment, a catastrophe of unimaginable scale occurs. The outer layers, which had been falling inward, bounce off the collapsed core like a ball off a wall. And they fly outward at several thousand kilometers per second. This is a supernova. A single supernova can outshine its entire host galaxy for several weeks. An entire galaxy of hundreds of billions of stars dimmed by one single explosion. And at the center, what remains is either a neutron star, an object of incredible density, where a teaspoon of its material weighs billions of tons, or a black hole. And everything that was in that star, all the carbon, oxygen, iron, gold, scatters through space, to one day become a new nebula, a new star, a new planet, or a new human being. This is where the most important part of this video begins. The part I want you to remember. Look at your hand. That skin, those bones, the blood flowing through your veins, where did all of it come from? Ultimately, if you trace the chain all the way back from stars, the Big Bang created only hydrogen and helium, nothing else. But your body contains carbon, oxygen, nitrogen, calcium, iron, phosphorus. None of that existed at the moment the universe was born. All of it was created inside stars. The carbon in your cells was synthesized deep inside dying stars. The oxygen you're breathing right now, same thing. The iron in your blood, it may have been in the core of a star that exploded as a supernova, scattered itself across the galaxy, and billions of years later that material came together again, first into a gas cloud, then into the solar system, then into the Earth, then into a protein, then into you. The astronomer Carl Sagan said we are made of star stuff. And that's not a metaphor. That's literally chemistry. Even the gold in wedding rings, even the silver in jewelry. These elements are so heavy they couldn't have formed even in ordinary supernovae. They're created by neutron-star collisions, some of the most extreme events in the universe. In 2017, such a collision was detected for the first time, and scientists confirmed in the moment of that event, gold was being created. Literally, in real time. Every element in you has passed through several generations of stars. You are the result of billions of years of stellar evolution. Not figuratively, chemically, physically, molecularly. That changes something about how you look at the night sky. Here's one more thought that I really love. We're used to thinking of the universe as something behind us in the past. The Big Bang, the first stars, the galaxies, all of that happened, and ahead only fading away. But that's not right. According to astrophysicists, the universe right now is not in its old age. It's more like early morning, maybe the first hour after sunrise. Most of the stars that will ever exist haven't been born yet. Red dwarfs that are only just now beginning to ignite will burn for trillions of years. That's thousands of times longer than the current age of the entire universe. In the future, when our sun has long since died, when our entire galaxy has changed beyond recognition, those tiny, dim stars will still be shining. The gas in galaxies is gradually turning into stars, but the process isn't finished. We are roughly in the first 10% of the universe's stellar era. There are 9 more such epochs still ahead. Of course, trillions of years from now, everything will slowly fade. The last red dwarfs will go out. Black holes will evaporate through Hawking radiation. What remains will be cold, dark, expanding emptiness. But that's so far away that the numbers lose all meaning. It's not frightening, it's just very, very far off. For now, the universe is young. And somewhere right now, in some gas cloud in a distant galaxy, a protostar is collapsing. Millions of years from now, a new fire will ignite. We started with you lying there, looking up at the sky. Go back there for a moment. Those lights above you, they are not just beautiful. Every single one is a nuclear fusion reactor that has been burning for billions of years. Every single one was born from darkness, from compressed gas, from chaos. Every single one will die someday and scatter itself across the cosmos. Some of them are already dead. You're looking at light that traveled to you for hundreds, thousands, millions of years. While that light was making its way to your eyes, everything happened. Civilizations rose, wars were fought, discoveries were made, people fell in love. And the star had already exploded long ago, you just don't know it yet. And you look at all of this and think, I'm so small. My whole life is just a flash. That can feel frightening sometimes, but you can think of it differently. The atoms in your body have survived several generations of stars. They were in the hearts of dying giants. They were scattered by supernova explosions. Gravity gathered them back together. They passed through a planet, through water, through billions of years of evolution and assembled themselves into you. You are not an observer of the universe. You are part of it, just like the stars in the sky. And you know what? I think that's a pretty good reason to peacefully go to sleep. Good night.